I'd like to start by reiterating great respect for First Nations people and culture, particularly in a conversation where we're talking about the imperative need to reduce our own embodied carbon. I think it's very relevant. A huge thanks to Ross for putting together a great series, and for the Institute for recording, and for Perth Design Week for putting a great show on generally. It was a very generous introduction by Ross to start with. I would really just describe myself as a nerdy builder. I finished architecture, turned to the dark side almost straight away, and have been a residential builder of architectural homes, and have been building homes for 15 years. I fell down the embodied carbon hole in about 2009, where I really started to ask the question, I'm a builder, what am I going to do? I'm pouring slabs every day, how can I do my bit? And started measuring, and once you start measuring, poking around, and you've got your little Excel thing in the corner, you realise there is a massive amount of information out there, you don't know where to start, and you slide down the hole pretty quickly. So I did that nerdy thing, and I had a few projects, and I built a little app where I was measuring how much shit was coming onto site and could sort of pin down the delivery drivers and ask them where they'd come from so I could calculate emissions. And the general consensus was, well, yeah, mate, where do you want the bricks dumped? Was kind of the feedback, because literacy's, quite low. And in that particular project, not to say anything disparaging about delivery drivers, but the carbon literacy more broadly, I'd say, is low. In that particular project, I said, all right, we've got the job, you beauty. How about we think about screw piles? How about we think about changing the external wall system from double reinforced block to a lightweight system? We could do some engineering tweakings. We managed to pull down 60% of the embodied carbon, and we had a cost decrease because it's quicker for me to build. Now that was all good. However, the feedback was, thanks, love your work, great stuff, but we can't redocument because it's going to cost us. It's already engineered. We're going now. Thanks, we'll just stick some trees in. And that was where I fell down the hole properly, thinking, okay, there is a problem here systemically with an architectural firm who was interested in environmental stuff, a client who was engaged with it, the builder was engaged with it, and yet we ran into that hurdle. Cut through to where we are now. I started Carbon Trace last year off the back of that carbon nerding that had been rattling around in my head for 5 years. And where I'm up to now is how you build the link between embodied carbon or greenness and the financial sector. Once you start to connect dollars with greenness, you really have a starting point. So today I'll talk about the live solutions and what you can do as a designer, and report on the optimistic progress from down the bottom of a hole, which some of you, hopefully come down the hole. It's a great place, but it can be pretty overwhelming. So come up for air every now and then. Otherwise, you'll end up talking with Ross at the Perth Design Week. So I'd just like to start by saying the commercial sector and the residential sector are different beasts. And we've heard of the rest of the series has been commercial sector focused. I am a residential builder building 1A, like one-off homes, and that is a bit of embodied carbon that really needs to be talked about and come to the front of the conversation, because it is getting left behind. And it is the urban sprawl and the mum and dad home is a very different paradigm to a project where there is a consultancy team, where there's a whole lot of backup and resource and energy, when it's just you as a designer, a project, an Excel document, and the web to get your embodied carbon modelling done. It is fundamentally a different landscape. 1A building stock. We need to build 200,000 homes every year for the next 5 years to reach our housing shortage goals. It is a sector that's dominated by fairly low sophisticated organisations potentially, tradespeople. There's white collar, there's blue collar, and there's no collar, as I affectionately refer to some of the builders that I've worked with. There's also a fundamental difference in that, suburban homes or 1A stock broadly has a fairly common typology repeat, particularly in that volume space. And really, from a bang for buck point of view, this humble home here is a different beast to the architectural one, but actually this is what's doing the damage. There's, our little architectural world has got a percentage of it, and architectural design stuff has a great need to really push the bundle in an embodied carbon space. However, you need to have scalable ideas and scalable solutions that start to engage with everyone, rather than just sort of have this cottage industry, really hardcore LCA analysis of a few things. You need to get the whole world talking about this. So I'd say within the residential sector, there is a sector within a sector. The need to measure, and I think Ross is if I'm a carbon nerd, Ross is a measurement nerd. And I think it's a good, happy place to be. And I think measurement is a design tool. Like, we need to understand if design is a series of compromises that are being made, unless you have measurement as a tool, you can't make informed decisions, particularly when they come down to embodied carbon and therefore cost. We really need to be measuring embodied carbon, and that's what this series is all about. Rules of thumb are great, and rules of thumb have been around since we've been building homes, really, but they need to be backed up with numbers and a metric. And at the very, very high level, embodied carbon, our carbon footprint, and LCA analysis, modules A1 to A5, B, C, D, that's great. What it comes down to really is how much stuff have you got and what's the impact of the stuff? And stick those two bits together, and you get to sort of, that's where you get to your impact, your embodied carbon. And when it gets really complicated and you get confused, I find that sort of dumb builder's logic, work out how much stuff you're using and then the emissions of each bit of the stuff, as being a way to sort of bring it back to the world. And I'd say the amount of stuff in a building is very much the domain of the designer. And understanding the impact of the stuff and the intricacies of system boundary and what you're analysing, what's going to happen to the project in 50 years in landfill, is a very relevant bit of subject matter. But that is the realm of the expert, the specialist. And I think we have to appreciate that as designers or builders and practitioners, we should focus on what we're good at and what we're capable of doing really well, which is measuring the amount of stuff in buildings. And that's certainly where I began my journey. Literally count bricks. I mean, in the embodied carbon world, where no one can agree on how much carbon impact a brick has, or how much carbon impact a cubic metre of timber has, that is all totally elastic. The only thing that is a real truth is that there are X number of bricks in a home. There is X amount of concrete, and there's 400 lineal metres of flooring, and where those sort of hard points form the foundation of measurement. From that, you can apply your impact factors, and you can start to get down to the landscape of how you factor in recycling. But sometimes don't get overwhelmed. It is just about the amount of stuff. There's also, and I think the other presentation touched on this, the idea of designing out carbon rather than specifying out carbon. And designing as being the bit where the fat red pen and the crayons are out, that's where the big savings are being made. Specifying out later by dropping in low carbon concrete, great, excellent, has to happen, but that should be a secondary consideration. And I think the key is early design decisions, and that ties back to where I started 2019, asking, have we thought about a screw pile solution to a site here? Like, from a build point of view, that was great because we were next to adjacent footings and avoided underpinning and all that. But how can you start to engage at that feasibility stage with the implications that might come about of one decision over another? And again, this mimics the commercial sector paradigm, which is the structural system, the outside of it, the footings, the envelope, is doing the guts of the work. If you start by measuring concrete, steel and masonry and get your outside of a residential building calculated, you're 60% of the way there. You can get really lost really quickly when you start trying to work out how many litres of paint are in a room, how many coats did they put on, you can really get down the hole quickly. And that's great, and that's the role of an LCA analysis, conducted fully and comprehensively, but that's not a scalable analysis mode. And where I've sort of ended up in my journey is saying, look, let's pick up the big stuff first, the low-hanging fruit, the stuff we can get our hands on, and then worry about the finer detail later. And from a designer's point of view, if measuring is the key and understanding how much material is in a project, then really it's about having access to that measurement at a very early stage so that you can make those decisions at an early stage with real numbers. I think it's of less significance to get to the end of the project, building's about to start, all right, now we'll do an analysis, we can do full takeoffs and work out how much material there is. Actually, we've missed the boat, and those decisions, they've flown the coop. So the challenge for designers is how do you have a data flow of relevant, project-specific material quantity at very early stage. When a design has to be dynamic, you have to have that fat red pen going. How can it be accurate? And more importantly, how can you be looking outside of your office and saying, hey, here's the measurement we get. What do they get? What do they get? Because if 10 people are measuring buildings in different ways getting different results because they're measuring in different analysis modes or with different emission factors, suddenly you start to undermine the credibility of what it is you've done. You get 10 different answers, well, which one's right? And it may be that none of them are right or wrong, but depending on how zoomed in you get on the analysis mode, you might get very different results. So what we've come to the point of realising is technology is getting good at measuring at an early stage, and we've been trying to leverage that through Carbon Trace, which essentially started off as a bill of quantities tool for that early stage optioneering, allowing designers to see, yeah, actually on this job, because the soil's rubbish, because we're in Brunswick and it's 3 generations of rubbish tip before we get into clay, screw piles would be a really good idea here rather than digging 1200 mil. So that's where it started. And then we realised, and the way it worked essentially is design teams would put in very rudimentary building envelope values, floor plate, wall area, and get a carbon output for different structural types and material types. What happens if you change from brick veneer to weatherboard? Oh, bang, 2 seconds, there's an output. All right, well, I'll put that in my little red pen. We evolved that to realise we could run that from a NatHERS certificate. And for those who aren't aware, a NatHERS certificate is a mandatory part of a building permit. You get an energy consultant to prepare a certificate that says your building envelope is compliant with the National Construction Code, got enough insulation, and so forth. Now, a NatHERS certificate will basically measure heat flow through the envelope of a building to see how warm or cold the building is. Sweet. We were not interested in that heat flow. We were interested in the material assembly that is just defining that heat flow. Because a NatHERS certificate tallies up the areas of external walls, the areas of floor, internal walls, all that is physically entered by a person at a project level. That means you've got an amazing set of project-specific data. We went to CSIRO and said, hey, we've got this thing. And they said, oh, this is pretty interesting. And then we entered a license agreement to process every NatHERS certificate that has been produced. So that's 6 years of data, 1 million data points, and we ran them all through our algorithm. And what that got us to dial into this, each grey dot is a postcode, and behind those postcodes sits that 1 million data points of property information. So from that we plotted, and our algorithm plots out intensity per square metre against the area of the house. And you can see here, this is a 70 square metre house, and it's got a really low embodied carbon intensity. And there's a few real bangers up the top there, and the guy who did that one's in trouble. But the point is, you can start to see, that's 1 million data points. That's every home built in the last 6 years, splattered out on a graph, which means you can start to plot the average. Once you know the average, you've got a benchmark. Then you can say, all right, if we're just analysing with a NatHERS scope, I know my building is here. And that's my NatHERS certificate compared in exactly the same way to 1 million other NatHERS certificates. And that then means you've got a way from a designer, and the way the tool works is you play around with very basic stuff. This is the low literacy stuff, trying to make it accessible to everyone. You play around with these features and you get performance shifts.
Can you just explain what happened there?
Okay, yeah. Familiar to you. Yeah, true. I bet, yeah. Too deep. So you play around, you can drop down with, again, the commonplace wall types, ground floor structures, roof, and all the various material groups. You can change the suppliers, and that's got some EPDs behind it with low carbon concrete, low carbon brick, and what have you. And then you modify those, and I'll show you on the next slide. There's a button where you calculate, and it will spit out a hotspot analysis, and it'll give you an absolute value derived from that NatHERS certificate. You fiddle around with these numbers, press like what happens, and you start to see a metric change.
Maybe better explain an EPD as well, because not everybody will know what that is.
You're right. I'm too nerdy for this. So an EPD is a way of measuring the carbon impact of a particular material that's been prepared by, say, a concrete supplier. They will analyse their particular concrete blend and say this has got an impact factor of 300 kilos of CO2 for every cubic metre of this concrete that we sell. And lots of suppliers are starting to get on board with producing lots of EPDs, and we're using that so you can, if you start to play around and use one of Boral's alternative mixes, it has a different emissions factor. So it can show you what's starting to happen if you change suppliers.
Stands for Environmental Product Declaration.
The short answer to EPD. We did a full analysis to see how much of a NatHERS certificate we were picking up. And again, it's sort of aligning with that commercial story, which is we're getting the guts of it in that superstructure and that external facade system. And that's the bit which Carbon Trace is doing. So a NatHERS certificate will give you an LCA analysis on any building type with a NatHERS certificate. Does it work on the really unglamorous bit of the 1A building stock? Because theoretically, an architect should be able to get a client to get an LCA consultant on board, do a full analysis, no worries there. So here what I've done is gone back to that house, taken off Google, roughly modelled its areas, and that's kind of where it lands, its NatHERS certificate. I don't have its actual NatHERS certificate, but I've got the input fields which would reflect what it would be. And that lands about where you'd expect, about its benchmark. And that intensity there is 157 kilos, roughly 33 tonnes for its absolute value. If I change from brick veneer to metal clad, I've essentially removed the brick bit of the equation. Brick is a relatively high intensity thermal mass embodied carbon product. So let's get that out of the equation for now. Change to metal clad, and you can see that there's a shift. And if you change to fibro or timber, it equivalently maps that, and you literally see your orange dot start to move in a downward direction. You change from waffle pod to strip footings, that is, you're getting a lot of the concrete out of the job, you're starting to see it drop right down. That should be triggering all of the design questions you should have. Why are we going strip footings? Why wouldn't we? Why would we go concrete? Why wouldn't we? But at least you've got some numbers and you can see like there's actual material change in those big decisions, which you might otherwise just be like, oh yeah, waffle pod, no questions asked. If you don't want to change anything, you want to keep it really simple, you just want to change supplier. If you change to a low carbon concrete, a 30% blend, that was, I think, what John was talking about, you'll get a 10% reduction. That's a phone call, and that's dropping in the specification. We either want this supplier, or it might be, we don't care which supplier, but they need to have an emissions factor of X, and you work out what that is. And that's where EPD data comes in. You do the same thing for brick, and so you're keeping your brick veneer on a waffle, but you've changed to a low carbon brick supplier. You've asked the question of a supplier. They've said, oh, I don't know, do we have an EPD? Doesn't he play for Hawthorn? Like, those sort of things are going to come out of it, which is great, because you're then extending the conversation beyond, our little world. And if you push those questions up the supply chain, that's how change happens more broadly. So takeaway from that is fiddle around with the structure and the envelope, because that is the big ticket items, and you can do that quite quickly for serious, meaningful results. And you can also start to change specification if you want to do nothing else, and that'll help. And I think the literacy was the key thing there. But I want to talk now, and this I need to see, how are we going for time, Ross? Okay. There's a reason why measuring has become relevant. And it's no longer just us thinking, yes, we want to build low carbon. Yes, I've got my little goals and my little Excel spreadsheet. There are two things which fill me with great hope in the short-term future that big progress is happening. The first of them is mandatory corporate reporting is changing. That means big businesses, that means banks, that means developers. Big end of town is now mandated to report on their scope 1, 2 and 3 emissions. Now what that means in real terms, I'll zoom out, scope 1, 2, 3, they're your organisational carbon impacts, I suppose. Scope 1 and 2 is pretty easy. How much diesel do you use and how much power do you buy? And scope 3 is everything else. And for banks, part of the everything else is anyone they lend money to is their problem. They have to report on that, their loaned emissions in a particular way. Same with anyone else attached to building. Volume builders, the big guys, the developers, they are all now having, their board is now having to report on embodied carbon in the same way they have to report on their financials. And if they get that wrong, they get sued. So the board is corporate boards are getting very worried about how they are going to approach scope 3 reporting, which is essentially scope 3 is embodied carbon. Let's use them interchangeably here. And the second big thing is there are lots and lots of pots of investment funds that have big bundles of money that can only be spent on green projects. And I'll talk on both these things in more detail in these two slides. So embodied carbon reporting is coming next year. Might get pushed to 2026. Read that guide. It's a ripper. And if any director of a big organisation hasn't read it, they should. Essentially, the big end of town has to get their heads around numbers now. They are liable. They need to measure. Now, they're not in the business of building homes. They don't know anything about it. They don't have any data. They are not close to any bit of information about embodied carbon. This is why they're worried, because there is not a data flow at the moment of scaled embodied carbon information going up the food chain. So they're worried. And the second bit of the equation, this is the green bonds. And this blew my head a little while ago, and it did take me a while to digest. So apologies, this is a dump. But there it is. You're all smart. You'll work it out. Green bonds, that is, our super funds, institutional investors are being told by their members, do not invest in fossil fuels, invest in sustainability projects. Super funds are saying, all right, that's what they want, that's what we'll do. So they've now got big bits of money that they cannot invest in anything other than sustainability. And these pots of money, the pots are getting bigger because more people are asking for this sort of investment. This green bond, as opposed to a normal vanilla bond market, is changing altogether. And what that means is there is now cheaper green money. And there's a bigger pool of global investors with pots of money that is earmarked for sustainability projects. So on the one hand, this is why I'm excited by the landscape. On the one hand, you've got big end of town needing to measure and get data on the stuff that they're attached to. And on the other hand, green money is getting cheaper. So people understand numbers now, and they know that if they can show something is greener, well, it's cheaper for them to borrow money to get it. And that's a big shift. But the problem is if you can't measure something, you don't know if it's greener. So importance of measuring is paramount. And that's my next slide. So most importantly, and to contextualise that a bit, you have to be able to measure it in a way that the banks can audit it. It has to be robust data. It has to be consistent. It has to have a methodology that will stand up interrogation from ASIC, the guys that look after all the big companies, because they're going to be the guys saying, hey, is that greenwashing? Are you sure that's greener? And if they're wrong and they're making a claim like, yeah, this is heaps greener than it was, and they don't have a methodology behind it, that's a big problem. Greenwashing is going to be the next big ticket item, I think. And what that's looking like is at top end of town, banks have realised, hey, if we can measure that the projects we're loaning money to build are greener, we can borrow greener, cheaper money for that little package of projects. And with that money, well, we got a few more profits, and I know banks have got their back against the wall, they're really skint. But maybe they could stretch it and expand their green loans offering so that ultimately mum and dad get a better mortgage because they've said this home is the one we want, and we want it because it's greener. And we know that if we can get, this is back to our NatHERS thing where we're coming in, that's all of them. This is our project here. Hey, bank, we've shown you that we're 30% below, we're performing better than the rest of the country by 30%. That aligns with the eligibility criteria of a global metric called the Climate Bonds Initiative. Write that one down, that's a really good one to know about. Which means, hey, designer, if you can get us in this green bit, we can go to the banks and we've got a way of saying we can prove that we're a greener home. And that means the banks are like, okay, you're beauty, we'll put you in our green pot and we can get some better money for that. And then hopefully that gets passed on to the mum and dad. So I think the main thing, and that was apologies because this was a segue off measuring, but really relevant to contextualise the meaning and the reason to measure, I think. It does all start with the nuts and bolts. It does all start with counting bricks. Don't get too overwhelmed because it's easy just to turn off and be like, hey, this is not core business. I'll worry about it when I have to. The reality is the have to bit is now for the big end of town. So businesses are now saying, hey, I can be a better business. I can make more money as a lower tier business if I am ready to engage with the needs of this upper tier corporate organisations. So it's shifting from ideology to dollars, which is what's going to turn everything on. So yeah, quantify the carbon impacts. If as a designer, just start measuring bricks, concrete, steel. At how much, not at a cost level, at just how much physical material am I putting in? Then dip your toe in the EPD world. Then ask the question about, well, what do I think about carbon offsets? What do I think about biogenic carbon? What do I think about end-of-life recycling? All of those big questions, have them, but start somewhere sort of easy. Don't try and boil the ocean, just do something and start somewhere. Thanks for listening. Apologies.
Well, that got serious, didn't it? Very grown up. Starting with a small house building enterprise and ending up in the world of green bonds and financing and all the rest of it. Quite a trajectory for a young man. See what you can do with 1 million data points. Crikey, and build a whole new world on the basis of it. Well, that was fantastic. Thanks, Tom. Quite a juxtaposition to the previous presentation, taking us into that front end of finances and single residential houses out there in the suburbs. So we've got a few minutes for questions. We haven't quite used up all of our time, but we have sort of run over a little bit. But are there questions? Oh, you asked one yesterday. So there you go. Didn't you? You didn't.
Thank you very much. It was awesome. More of a discussion point. Does anyone know of any QSs working in the commercial sector who are embracing this as part of their core service? Because everything gets measured. It's just a matter of plugging in and connecting it to the data instead of more people doing the same thing inconsistently.
Lots of them, actually. You want to...
Look, again, it's not really my 1A stock doesn't have too many QSs attached to it. So therein lies one of its big problems. So
they are rushing into this territory because they measure. They measure quantities. It's very easy for them to plug in an EPD database on the back of that, and they can give you a carbon. So QSs are. There are 2 or 3 in Perth I know who are really jumping into this territory.
Which ones? Because we're yet to have.
Can't find one yet.
One's approaching us saying, "Hey, we're ready. We want
Yeah.
to do this. Here's the service. This is what it costs."
Yeah.
Let's get it happening.
I mean, to give you an example.
We've had to engage a couple to go
Seems
back.
slow.
Oh, you're supposed to be speaking into a mic, aren't you?
sorry.
Not doing my job.
Hi, Mark from Hesperia. And we've worked together on a couple of projects, but we have had problems with this because you get to the end of the project and you don't have the data, and you've already committed to net zero on that project, whatever it is. So we've had to engage QSs to forensically go back and figure out what was in the building, because nobody knows. Like, it's unbelievable, but nobody knows what's in a building unless you ask them to record it. And so, yeah, we've had a couple, like WT partners.
Ryder Hunt, whatever they're called now. They used to be Ryder Hunt. Anyway, I can look it up for you. There are, give an example. So the diagram that we saw in the first presentation, which showed the various stages in the life of the project around whole of life carbon, that's a European standard called EN 15978, and that's become a sort of fairly universal, increasingly universal, and it's going to be the basis of the neighbours certificate process. And alongside that sits a guidebook for how to measure to support the platform, and it's written by the Royal Institute of Chartered Surveyors, so they're quantity surveyors. So quantity surveyors see this as their future, so it's coming at a rush. Daniel.
Just a question around the green finance and whether or not you've seen that happening, or is that sort of a projection or a forecast that you were talking about? So we've had some experience dealing with banks, both for developments and entirely timber projects, and we're only really getting 0.5%, which then when you factor in the cost for all the analysis and LCAs and measuring, it almost doesn't really kind of offset or cover.
Yeah, it's a relevant point. Look, the green loans that are out there, and it sounds like this echoes your experience, they are marginal at the moment. And I think that's because banks are not quite sure what this landscape looks like. They are not confident enough. Yes, they don't have the data flow yet. I mean, they don't have the data to accurately start to understand and package up large bits of their portfolio yet. They see the writing on the wall. They are crying poor. The CEFC, that is, the Clean Energy Finance Corporation, are in theory supporting and have a big pot of money that is also, they can dually go into projects with banks, but they're finding pushback from banks because they're like, oh no, look, we can't afford that. We're just the CBA. So I think at the moment there's not quite the literacy there. There's not quite the data there, but it is being talked by everyone. And it's going to take one of them to do it properly and get the data flow going. And then the big kicker for them is onboarding new clients. They're not really that interested in embodied carbon, whatever. They just want your money. So if it means they can get you in with a loan and onboard you as a new client, that's worth money for them. So if once they work out a way to connect it, and again, these conversations are happening like right now, it's only going to head in one way. So keep going what you're doing, because it will happen.
And just on this point about the measurement that happens later and not knowing what's coming, I think the key to that is having tools that enable you to do it rough and ready at the beginning, isn't it? So you can set yourself up for success, which Carbon Trace does. But I'm also, at the risk of overdoing one commercial enterprise, I'm going to ask Morgan to say something about the light and quick and easy upfront stuff that eTool has. Assuming I got that right.
Yeah, absolutely. I guess from an early stage analysis point, LCA's traditionally looked at quite a academic process, and you need how many nails and how many bolts are going into the building. But there is, I guess, business as usual assumptions you can use to build out early stage concept designs. So looking at whole of building templates essentially is the way that we do it, and you just put in simple input metrics like how many floors and how many square meters go into the building. That will automatically calculate things like concrete floors, foundations, services, lighting, to build out an in-depth model that then you can apply your hotspot analysis to at a very early stage. So
Make it more sophisticated as you go through.
yeah, and you refine as your data maturity grows. Yeah.
Thanks for that.
No worries.
Yes, you can. That's what I'm here for.
I'm actually a private person. We designed 4 times a home in the Netherlands. When we came to Australia, we bought an old home and we rebuilt it partly. So can we use things like this, measurements, a thing? Can you go online and measure it out? Because it's very difficult to find all the different information about all these carbon neutral things. We go to scrap yards and we use material that came from the house. But how can you find, because Bunnings doesn't say anything about that?
Yeah, really good question. So yes, I guess the Carbon Trace tool as it is now is driven off a NatHER certificate. So as its primary data source. But that said, we have a tool there where you can start to quantify at a elemental level how much wall you've got, and work essentially in your model, in that retrofit model. You might look at how much of the building are we keeping. That is, how much carbon have we not had to spend on that bit of it? How much have we had to spend? And the net area that your house is now, the size of it, is a product of only what you've actually had to bring in. So I'd say it's not a very articulate way to answer your question. I'd say Bunnings need to get on board and get EPDs, but also if you Google EPD Australasia, it has a database, probably our best single source of open source EPD data. You have to drill into it a little bit, but it is got a big catalogue of lots of different suppliers, lots of different products. Don't be overwhelmed by the fact there are 80 pages and most of it's tables. There's 1 or 2 bits in there which are the relevant bit. Work out one and you will have worked out all of them, is the way I could say it.
Hi everyone, my name is John Noel. I'm a structural engineer based in Melbourne, working for Arup. I'm an associate based in our Victorian structural or buildings team, and I also lead our Australasia Structural Engineering Sustainability Hub, and our decarbonisation portfolio for the region. I'm a Engaged Engineers Declare signatory, and I try on projects and in any of the work that I do, I try to challenge clients to first consider building nothing, building less, building clever, building efficiently before specifying low carbon materials. Our global carbon budgets. So if you look at this graph that starts in 1950, the sort of darker shade of blue that takes us to 2020, that's the cumulative carbon in the atmosphere. And if we are to meet our Paris agreements of limiting, warming to 1.5 degrees, global warming to 1.5 degrees, then we have to take drastic action, and we have to reverse the curve quite aggressively. So to meet 1.5 degrees, effectively we need to halve our current emissions by 2030 and get to net zero by 2050. So that's how steep the reversal of that curve needs to be to meet those targets. The construction industry, as most of you will know, is a significant emitter. We're responsible for approximately 40% of emissions globally, and that's broken down into building materials and construction at about 11%. The rest made up of buildings operation, so 28% plus 11, roughly about 40, which is significant. If we look at how that's broken down between embodied carbon and operational carbon, and we'll sort of explain the difference in a second for anyone who may not know. Currently, and it depends on the source, but this is according to Neighbours a few years ago now, 2019, the breakdown was approximately 16% for embodied emissions and 84% attributed to the operation of buildings. And that's very likely to change significantly as the grids in particular clean up and operational systems become more efficient. We're looking at a projection, again by neighbours, by 2050 of reversing that. So 85% sitting in embodied carbon or embodied emissions versus 15% for operational. And that means that embodied carbon, that was for a long time the sort of elephant in the room that wasn't being addressed because operational carbon was a larger piece of the pie. As that is now being actioned, that reveals the embodied carbon volume or size, and that needs to, or is going to grow relatively in terms of percentage, and there's a huge potential there for reductions. And as a structural engineer, talking to you about carbon reductions, that's predominantly what I'm going to be focusing on today, embodied carbon. COP27, Arup made a public commitment in conjunction with a number of other bodies, Race to Resilience, or under the umbrella of the United Nations, or this broader UN 2030 breakthrough group. But we made the commitment that all our new projects completed by 2030 will be net zero in operation with at least a 40% reduction in embodied carbon. And that's very much to try to meet on our projects, try to meet the demand for that curve reversal that I first showed. Again, halving our emissions by 2030, get to net zero by 2050. And we along with that statement or that commitment, we issued, in partnership with the World Building Council for Sustainable Design, a joint publication called Net Zero Buildings Halving Construction Emissions Today. So what is embodied carbon? I'll pass very quickly. I'll assume that most of you are aware. If anyone isn't, it's the carbon emissions equivalent associated with the whole life cycle of built assets, not accounting for operational energy, water use, or asset utilization. So if we take those out, which are the dark blue groups on this image, you're left with the green colors, which is embodied carbon, and that spans across from left to right: product, construction, in use, and end of life. And then beyond that is a circular economy piece, or beyond the building. I won't go into too much detail other than focusing on A1 to A5, so the product construction stages. I might as well break them down now. So A1 is raw material supply, A2 material transport, A3 manufacturing. So it's all the energy and therefore emissions associated with those processes. And then construction under A4, we've got product transport, and A5 construction and installation. And that's a international recognized standard. So if we all talk the same language, then we can agree or disagree on quantities, but at least the framework is consistent. So what does that look like across the timeline of a project? In red is the carbon, and blue, and sorry, in grey, the offsets. I'll pass on the offsets. If you focus on the red above the baseline, then that first sort of peak is the energy and therefore the carbon that goes into the construction and the products and processes involved with your building. Following that operation, so there's an influx of energy and therefore emissions until you get to your first maintenance or replacement or refurbishment, and there's another peak there in carbon, and so on and so forth until you demolish and dispose of the building. And then there's energy associated with that process, plus energy and carbon associated with material reuse, so transport to the new location, etc. And at the bottom of that graph, you'll see obviously the different stakeholders for those different processes. I think this is all pretty self-explanatory. Now let's jump in a little bit into what makes up embodied carbon in a building. This is a source from LETI, which is UK centric, let's say, London Energy Transformation Initiative. But it is representative. We certainly in Victoria find that the numbers are very close. And typically for a medium scale residential, you're looking at about 2/3 of the embodied carbon sitting in substructure and superstructure, and the rest made up of internal finishes, facades, MEP, and that in different proportions, whether you're looking at medium scale residential or office. The proportion of MEP versus finishes, for example, will switch depending on whether it's warm shell, cold shell, etc. But I think big picture, we're talking about 2/3 of the embodied carbon sitting within the structure, about 15% with facade, and then the rest between MEP and finishes. So where does that carbon come from? Well, mostly from the production of the of the materials that make up the elements that we use in construction. So steel contributes to about 6% of the world greenhouse gas emissions. And if we look at where those emissions occur, there's emissions associated with mining or procuring recycled steel, but the bulk of the emissions sit with the process of manufacturing the steel. So if you're using a blast oxygen furnace, the chemical reaction and the fact that you're heating up the steel that's the energy hungry process, and that's where most of the emissions can be attributed to. If you're using an electric arc furnace into which you feed recycled steel, that's typically 50% more efficient, but it is still energy intensive, and then the rest is made up transit, use, end of life. Just back to the blast oxygen, BOF versus EAF. In Australia and worldwide, it's about 70% for blast oxygen furnace production, and about 30% for electric arc. Concrete, that's about 8% of world greenhouse gas emissions. Similar story. There's some energy in there for carbon associated with mining the raw materials. The difference here between steel and concrete is that in addition to the energy that you're feeding into the process, the chemical reaction to manufacture the cement releases CO2. So not only pumping energy and CO2 into heating up the kiln, you're releasing CO2 as part of the chemical reaction, which is why concrete is such a strong emitter as a material. And then similar to steel, the rest is then in getting that product to the mixing, the batching plant in the case of concrete, and then transit to site, etc. Timber. Well, timber's very different in that it sequesters CO2, as you probably all know. So it's a carbon sink, but then through the life of to get from the tree to the engineering product, you have to log, you have to take it to the manufacturing facility, you have to transform it, then transport it to site, erect it, so that there's energy and carbon associated with all those processes. So the logging, mill residue, biomass, and fossil fuel from the manufacturing, and they all add up, but they still don't add up to that's still less than the amount of CO2 that's sequestered within the timber. We'll talk about that sort of equation a little bit later, but that's obviously the fundamental difference between the three typical materials that make up a structure: steel, concrete, and timber. So what are the reduction strategies that we can employ to halve our embodied carbon emissions? The first one we tend to use is one that's suggested by the Institution of Structural Engineers. It's a very simple diagram or process. It's basically to use less stuff, and I'll expand on that in a second. And that's your primary focus. Once you've exhausted all those avenues, then you specify low carbon materials. And once you've exhausted that, you offset as the absolute last resort. And if I expand on using less stuff, there's a hierarchy that we like to step our clients through that hierarchy, starting with the question, do we need to build something? Can we build nothing? So challenger brief, is construction the answer? Following by, can we build less? So can we repurpose, refurbish, reuse, maximize space utilizations? Or, and again, stepping down, can we build clever? So what are the appropriate structural configurations or the appropriate design criteria for this particular project? Build efficiently, so high utilization of structures and use carbon efficient materials, and finally minimizing waste. And I'll be illustrating what this process looks like on a couple of projects later on. So if you look at reduction strategies in layers, if you look to the diagram at the right, that's sort of looking at the onion that is a building, from the site that it sits on, and then you've got the skin, the structure, services, space planning and stuff. And it's sort of like unpeeling the onion, and looking at those different layers. And looking at those different layers, if you look at the graph to the left, vertical axis is impact, and the horizontal axis goes from the left to sort of holistic big picture, all the way to the right, sort of specific across those building layers. And you'll see that the build nothing question, of course, has the highest impact in terms of reducing your embodied carbon. It is confronting for a profession that makes a living from building things or designing things to be built. But I'll show you an example of where we worked very hard to eventually build nothing. And that's a fantastic result if you can do that. And I think the rest is self-explanatory as you sort of move away from that and you start to look at repurposing, or build efficiently, or looking at your building height or your area efficiencies. Then the impact diminishes, and then it gets more and more granular. You start looking at design for disassembly, looking at the different layers. Those same reduction strategies then in time. This curve shows your diminishing opportunity for leverage or change. So at the very start, you're briefing, you've got 100% potential, let's say. This is where you ask the question, build nothing, or reassess the need, or basically that sort of upside down triangle that we had on a few slides before. And as you progress and you get more and more stakeholders involved in the project, your room to maneuver obviously diminishes. So there's certain questions, you don't wait for the contractor to be on board to ask the question, can we build nothing? That's sort of what we're saying here. But you can ask relevant questions at every stage. So you get to construction and how can we build leaner, for example. So back to structure. If you look at the typical breakdowns in a building, this will vary widely depending on soil types, for example. So take all of this with a pinch of salt. But typically, you're looking at about 70% of the embodied carbon sitting in the floor plate structure. The rest being made up of your vertical structure, plus your columns, your core and stability system, which is about 12%, and then the rest between substructure and foundations. So the biggest bang for your buck is really to look at the floor plate structure as a priority. If you do that, you realize that for typical spans for typical floor plates in a building, let's say a commercial office, then for that typical range, you can go from 1 to 2 in terms of the amount of carbon that you put into that system, depending on 1, the span, and 2, the structural typology. And you can see the graph to the images to the right there show that not all structural systems are equal. You look at RC, reinforced concrete flat slab, for example, that's probably the highest in terms of material and therefore embodied carbon, sitting at close to 300 kilograms of CO2 equivalent per square meter. And the more you dematerialize the system, So looking at rib slabs, for example, or waffle slabs, obviously the less material you use and therefore the less carbon. So those are strategies that we like to employ or deploy on projects, trying to dematerialize the floor where we can and try to reduce the grid where possible. Design efficiently, this is talking to looking at maximizing utilizations of elements, interrogating the serviceability criteria to make sure that that the response is appropriate. So, looking at facades or internal partitions, long span beams and deflection, dynamic criteria, crack width requirements, etc. Using bespoke criteria as opposed to generic. Refining the loading criteria and designing for use now and strengthening if use changes later. And I'll show you examples of this in a second. What I won't talk about today is low carbon concrete, because typically that tends to be the default. Let's reduce embodied carbon by specifying low carbon concrete. Of course, we can do that, and we do on projects, and I could do a whole presentation on where we're doing that very successfully. But I think my message to you today is that there are many, many things you can do before you get to that point, and that point should be the last on your list. And is timber the silver bullet? Well, it depends. So it's a very complicated graph, and we could spend probably the rest of the presentation unpacking this. This is again taken from that publication, and there's some detailed explanations as to how, what this all means. But the big picture message here is that timber used inefficiently, and I think we can all think of buildings where a lot of timber has been used possibly inefficiently. The carbon story is not necessarily as good as you might think. And in fact, there are many studies that show, if you look at the blue dotted line, there are many studies that show that timber used inefficiently could have a higher embodied carbon per square meter than an efficient post-tension concrete or steel concrete composite system. And this is despite or considering the two main things that I won't have time to unpack today, but need to be considered for timber. One is sequestration, so the fact that you've locked the carbon into the timber. So there are two considerations here. There's the time value of locking that in now, because now is when we need to take carbon out of the atmosphere. So even if you were to release it at the end of the life, there is still value in locking away that carbon. And of course, the second thing is what happens at the end of life. Does that carbon get released back into the atmosphere? There's no alignment yet across the industry. Arup doing a lot of work to try to put some numbers and some data and some testing to show that even if you bury the timber in the landfill, it doesn't release 100% of that carbon, and it releases far less than is assumed. So my message here is that timber is fantastic, but it needs to be caveated. It needs to be used efficiently as a material, and the considerations for sequestration and end of life need to be very well understood for that carbon accounting piece. Okay, so let me move into some practical examples. How do we influence the brief? Day one, blank sheet, sitting down with the client. In this case, I can't tell you the name, but it's a hospital in New South Wales. It was the base case for future hospital developments in New South Wales, looking at how we can brief the embodied carbon associated with the structure. So we did a whole bunch of benchmarking, looking at current designs, and then produced a list. This is one extract of a very long report. I don't expect you to read the text there, but I'll just pick a couple of examples to show you example of measures that we're suggesting. So typically 30% sub SCM, so Portland cement replacement, was used. If you go from 30 to 40%, then that's a 2% reduction in structure overall. Sounds like nothing, but it all adds up. 8, for example, switch to bubble deck for suspended floors, and you get a 6% reduction in structure, 3.5% carbon reduction overall, all the way to some very aggressive use calcined clays for all concrete. That's not mature yet, but in the future, 5 to 10 years down the line, it's likely to be mature enough that we can use that in Australia, and you're talking about a 25% reduction there for structure alone. So that's an example of how, before there is a project, we can start to suggest ways, and that can be baked into the brief that then goes out to consultants for these projects to say, here are some of the measures that we would like to see on the project to reduce embodied carbon. Build nothing. This is an example where, for the La Trobe campus, La Trobe University here in Victoria, in Bendigo, we looked at a couple of buildings that are about 50 years old, constructed in the 70s. The university thought they'd come to the end of their useful life. There was a full audit of the structure carried out that we inherited and were asked to come up with scenarios, and the scenarios being demolish and rebuild, refurbish, or demolish and do nothing and create a park and and decant the population from those buildings elsewhere on the site. And we put a lot of science into looking at those different options. And I'll just focus on the retrofit conversation. So the graphs that you see to the right there, the different tiers, tier 1, tier 2, tier 3, represent the range or the variability in interpretation of the seismic compliance requirements. In Victoria, and I'm sure it's the same in other states around Australia, it's at the discretion of the building surveyor what seismic load you consider for a retrofit, recognizing that 100% of the loads that would otherwise be used for a new building is probably overkill for an existing building. So tier 1, tier 2, tier 3 here represent the possible range from 100% to 33% of the seismic loads. And we basically looked at, for those different options, what the different structural solutions would look like, including jacketing of existing concrete walls, reinforcement of existing foundations, etc., and quantify the carbon that would be associated with those solutions. And we fed that back into a large matrix of options. Again, this is a very simplistic summary, but embodied carbon was one of the parameters, which you see in that column in red. And the summarizing 3 options: rebuild, refurbish, or park with low carbon infrastructure. Embodied carbon was just one of the considerations, but because we put so much engineering and therefore science into it, it sort of took out a lot of the uncertainty. So it became a real decision metric on the project. In fact, it was detailed enough that overall, holistically, the decision was made to demolish and move the population of the buildings elsewhere on the campus and create a park. So this is one example where we did a lot of work to eventually build nothing, and we're very proud of this little project. Build S. Probably familiar with this one, Quay Quarter Tower in Sydney. This is a 1970s skyscraper where we demolished a part of the existing structure, retained a large proportion, and then redeveloped the land where most of the demolition had occurred. That old building was no longer considered attractive to tenants, had 2 small floor plates, hence the project requirement to increase the floor. So that went from 50,000 square meters to almost 90,000, but 68% of the existing structure was retained in that process. And in doing so, we saved 12,000 metric tons of embodied carbon. If you put that in, airplane numbers, that's many, many trips, Sydney to London, just to give you an example. I won't go into too much detail here. I'm going to expand a little bit more on this one. This is an illustration of Bill Clever. It's a project in London, 18 Blackfriars, a large commercial tower. The first thing we did was to benchmark. So the idea was to use embodied carbon targets as the driver for most of the decisions across the project. But before we did, we had to agree on what those targets were. So we benchmarked. The Greater London Authority has some benchmarks and then some aspirational targets, and essentially the where we landed, it's a long story, but where the project landed was sort of close to the GLA aspirational benchmarks with a stretch target that brought us below that, which was definitely state of the art in terms of carbon per square meter, especially compared to other recent developments. So that benchmark for overall carbon then translated for structure to about 315 kilograms of CO2 equivalent per square meter. And we're able to break that down into the different components, looking at the target or the aspirational targets and what that meant per element. And then from this, we're able to improve incrementally to reduce carbon. So, but it has to be done from day one and holistically. It's a 210 meter tall tower, 48 floors. It's London, so it's constrained site. There's a BT tunnel in the substructure, for example. But essentially, the carbon targets led the design. And because the floor plates represent a large proportion of the carbon budget, it was essential that reduction was maximized. Transfers were minimized in the structure, and then the massing of the building was such that it led to efficiencies or carbon reductions by reducing the wind loads. Looking at the floor plates, the target was 35 kilograms of steel per square meter, which is far less than best practice, sitting at about 50. And to achieve that, we had to reduce the grid. So we're looking at, and this is a commercial floor plate, 9 by 9 and 9 by 6 in the lower levels. And then the high rise levels, 9 by 11.5, limiting the cantilevers everywhere to 3 to 4 meters max. And all of that was to basically talk to the efficiency, use less material, therefore less carbon. We're very clever in the assembly, so we use haunch moment connections to increase the efficiency of the floor plate to get us to that 35 kilograms of steel per square meter. Using also roll sections, which have lower embodied carbon typically, in lieu of fabricated plate girder sections that would have been used otherwise in areas of high demand. Load optimization, we did some benchmarking looking at other offices that were currently being built or recently built, and realized that most developers were building in excess of what would be reasonable for future flexibility. So it was agreed here that 2.5 kPa for the floor loads plus 1 for partitions would give enough resilience for the future, but also do its job now and in the future. But in doing so, reduce anywhere between 5 and 10% total loads, meaning that we were able to save 3 kilograms of CO2 per square meter over close to 100,000 square meters. So that's 300 tons of steel just by that simple measure, or 900 tons of CO2. And looking also at facade, we had the carbon budget drove a requirement of essentially 1.5 kilonewtons per square meter on elevation, which de facto eliminated precast or masonry facade. And that was the way the project functioned. The budget drove, the carbon budget drove the solutions. And that's a wrap on reducing embodied carbon in or halving embodied carbon and some practical examples as to how we're currently doing that on projects, honouring our commitment at Arup to reduce by 40% our embodied carbon on projects by 2030, which really means now, and how we're on that trajectory and trying to bring our clients on that journey for net zero by 2050. So thank you very much, and I hope you enjoy the next presentation and the conversation after that. Thank you.
Hi, everyone. I'm Dr. Natasha Watson from Buro Happold, and I'm coming to you from Bath in the UK. I am a structural engineer by training, but I'm now the embodied carbon lead for UK structures, and I've been in that role for around about 2 years now. What we're doing within Buro Happold is really trying to investigate embodied carbon within our discipline and ways that we can reduce it within our sort of designing, within the kinds of projects that we work on, etc., in line with our sustainability targets of reducing the embodied carbon of our projects, buildings and infrastructure by 50% by 2030. So I do several things from upskilling colleagues to working on advisory projects where embodied carbon is a key factor, and pretty much everything in between. Cool. My presentation to you today is going to be on designing carbon out, where I'll be focusing on reducing embodied carbon on projects. And it's a pleasure to present to you at Perth Design Week. So first of all, I'm going to give a very brief overview of what carbon emissions are for buildings and infrastructure. Whole life carbon emissions are the sum of operational carbon emissions. So these are the emissions associated with the operation of a building. So things like heating, power, probably air conditioning in Australia, a lot more, those kinds of things. And embodied carbon. So these are the emissions from the making, maintenance, and disposal of building materials. When we look at operational carbon and embodied carbon together, operational carbon emissions are reducing with the decarbonisation of our energy grids in many countries, and also due to more efficient building systems. So embodied carbon is already a much bigger percentage of a building's whole life carbon than before, and it will only continue to grow. To put embodied carbon into context, if you were to remove 25 millimeters from floor slabs of a standard concrete office, that's the same as going vegan for 70 years. So it's a pretty big impact that we can have as built environment professionals, even more so than us as citizens. And if you want to check my maths, those are all my assumptions below. Every ton of carbon that we emit adds to global warming. If we look at global CO2 emissions, to date, we've been producing around about 1,773 gigatons of CO2. That's from one source. And we then have a remaining budget of 250 gigatons of CO2. And that's what we have as our remaining budget if we want to achieve a 1.5 degree increase in global temperatures in our future. So how do I actually reduce embodied carbon on my projects? Well, first of all, we need to figure out where the embodied carbon is. This embodied carbon baseline emissions bit of research was completed by the London Energy Transformation Initiative in 2020. A bunch of really eager engineers based around London, based in many different engineering firms, and they figured out that approximately 60% of embodied carbon was attributed to structure. Hence me as a structural engineer being very interested in this, because what I see is that structural engineers have a very big part to play in embodied carbon reduction. So we are going to focus on the design decisions that reduce embodied carbon. To do this, we need to look at a conventional baseline building. This is the baseline building that we drew up when we put together our sensitivity studies, which is a a series of studies that we produced for the Institution of Structural Engineers back in 2020. We looked at what we considered a conventional office building, which had a 9 meter by 9 meter grid. It was around about 6 stories high at 4.2 meters floor to floor. It was four bays across, 4 bays deep, and had the following other assumptions that you can see on the right-hand side. We allowed 1.5 kPa for ceiling, services, raised access floor and finishes. We assumed 5 kPa for imposed loading and also movable partitions. These 2 loading assumptions are pretty standard within the UK. We also looked at keeping deflections to less than 20 mil. We also looked to keep the natural frequency of the building, so things to do with vibration, etc., to over 4 Hertz, which again is a pretty standard natural frequency aim for buildings. We also looked to have a 60-minute fire resistance. For the substructure, we assumed a ground-bearing slab, and we also assumed that we had thick, unreinforced concrete pad foundations. So no reinforcement in it, just sort of mass concrete to support the building. And also we assumed a 250 kPa bearing pressure with the soil underneath. Looking at this conventional baseline building, we then actually considered 3 different distinct forms. We had a look at concrete flat slab. We also had a look at composite slab on steel frame. So that composite slab is a mixture of concrete topping on a metal deck, and then all of that was on a steel frame. And then we looked at a cross-laminated timber slab on glue-laminated timber frame. With all of those assumptions and more, we came up with our baseline embodied carbon figures for these 3 baseline forms. For the concrete flat slab, we had a number of 349 kilograms of carbon dioxide per meter squared. For the composite slab on steel frame, we had 269 kilograms of CO2e per meter squared. And then on the cross-laminated timber and glue lam frame, we had 180 kilograms of CO2 per meter squared. So moving on to the first thing that you can potentially do to reduce the embodied carbon of your buildings, taking our 3 baselines, which had a 9x9 grid, as we saw before. If we reduce those across all 3 of those baseline options to 6.5 by 6.5 as the structural grid, we greatly reduce the embodied carbon. So the concrete option goes from 349 to 236. Steel option drops down to 228, and then the timber option drops down to 138. The reason that this happens is because floors are actually the most inefficient system within a building. And if we can reduce the amount that they need to span, you can greatly reduce the amount of material needed within your floor slabs. And this also greatly outweighs the number of extra columns that you need within the building for the same sort of floor area that you're trying to provide as well. Really reducing the structural grid has a very large impact. And if you change one thing on your buildings, I would really suggest reducing the structural grid. Maybe not even wholesale, maybe in key areas where you can really sort of justify it, because this, above all else, will have the best impact on reducing your embodied carbon. Another thing you can do is actually question your imposed loading and your serviceability. So we had an assumed imposed load of 5 kPa for our 3 options. And if you can really refine that to achieve 3 kPa across all the different options, you can also have really significant reductions in embodied carbon. This doesn't mean designing in an unsafe way. What this means is really trying to define and refine the loading that you're assuming within your building. This can be through discussing finishes with the project team early on, really sort of focusing on where key plant rooms will be located, so we can add extra material in those areas, but then remove it in other areas, different things like that, so that we can really sort of identify and realize the savings that we can make through putting the loading requirements and putting the material where we need it. Having a look at sort of imposed loading and serviceability, hopefully this then sort of leads to the fact that if you've got sort of lighter loading program, things like residential uses, hotels, car parks, cafes, etc., having them higher up in a building means that you're ensuring that you're not overly loading your columns throughout the whole height of your building. Maybe focusing on slightly sort of medium load requirements throughout the majority of your building. But I think the key thing is making sure that really heavy loading program, things like heavy storage, server rooms, plant rooms that contain chillers and water tanks, and keeping that on the ground is a really good way of ensuring you're not putting excess material due to not thinking through the program with embodied carbon in mind. Also, one thing that you can do is question adaptability. Typically, we look at adaptability as a way of thinking that we need to put initial redundancy throughout the whole building. So adding redundancy to columns and also redundancy to your floor slabs. So this might mean, oh, it might change use to let's say a dance studio in the future. So you kind of design the building with the possibility that it might become a dance studio in the future. When actually we should be looking at designing for the use of the building as it is now, only putting redundancy in the columns, but allowing for space for there to be strengthening measures within the slabs as and when a future change of use may happen. So if we look at putting initial redundancy into say a standard concrete frame building, we've got around about 349 kilograms of CO2e per meter squared. But if we actually design the columns to carry the initial redundancy that they need, but design the slab for the use that it has now, and then add the embodied carbon that you might have in the future for strengthening. In the case of concrete, this would be something like carbon fiber strips. You can save around about, a significant amount of carbon dioxide on your building, and also save in the future as well, because carbon fiber strips, when used appropriately, actually only really add about 10 kilograms of CO2e per meter squared of the concrete building as well. Another thing that we can focus on is structural depth. So within those three options that we had, we were looking at a concrete flat slab for the concrete option. We were already looking at universal beams for the steel option, which are an inefficient system anyway. And we were also looking at a cross-laminated timber or CLT deck for the timber option. For the concrete option, CLT option, we considered using a waffle slab, and also something called LVL on I-joists, respectively. And those reduced the embodied carbon of those solutions. Within the concrete option, it reduced it significantly. It's around about 50%. And then also we considered looking at universal columns used as steel beams within the solution. And this drastically increased the embodied carbon of the steel option. A lot of the time we do get pushed to really reduce the depth of beams within steel options specifically. And just to highlight how much of an impact this can have on your embodied carbon, we wanted to demonstrate it here as well, rather than just showing how we can even further reduce embodied carbon from a universal beam solution. Next, looking at materials. I think the key thing I want to get across here is that when you look at a material, you can't compare it on a per kilogram basis. If you look at this diagram that I have on the left-hand side, you can see that third from bottom, or joint last, concrete actually has a really low embodied carbon per kilogram. And then timber and steel are significantly higher. But what we need to consider is that actually, if you're using timber, steel, or concrete to actually span 7.5 meters for a given load. When you have a look at it, the timber option is actually the lowest embodied carbon because it weighs much less, even though it has 3 times as much embodied carbon as the concrete. Next, looking at material specification. For our concrete option, we assumed no cement replacement. We assumed a CEM 1 designation. That's what we call it in the UK. For steel, we assumed the steel having a strength of 355 newtons per millimeter squared, which is a pretty standard steel spec. And then for the glue laminated frame, we assumed it as having a strength of 24 newtons per millimeter squared as well. With each of these, we managed to demonstrate savings through either cement replacement in the case of the concrete option. 25% ground granulated blast furnace slag is what we assumed. The reason we assumed only a modest amount of cement replacement is because ground granulated blast furnace slag, or GGBS, is a finite resource. And if you over specify it, you're not actually saving the whole system embodied carbon. You're only demonstrating that you can reduce embodied carbon on your own project because you're taking that GGBS away from several other projects that could have benefited from it. In the case of the steel option and the timber option, what we did is we went up a couple of grades. So we looked at slightly stronger steel and then also a slightly stronger glue laminated timber as well. And the key thing that this demonstrates is that if you're working in concrete, steel, and timber, you don't need to wait for a new fancy material to come online for you to really make savings in your embodied carbon. You can do a lot with the materials that we have available now and specifying appropriately. Now we're looking at shallow reinforced pads. If you remember before, we had a look at thick mass pad for the foundations for the baseline. And actually what we found is if you make those pad footings a lot shallower and put in some reinforcement, you can show some savings in the foundations as well. This is because even though we are adding steel by way of reinforcement within the concrete, the savings in the mass of concrete that we're putting into the pad foundations are what actually give us the savings in embodied carbon that we see here. So those were all quite discrete interventions that you can make, but I think what the key thing is we try and put them all together within our designs, not just focus on one, but really try and look at the cumulative impacts of all of those different design decisions together. And then what we have is a systematic reduction in embodied carbon for all of those different options, which are significantly less than our baselines. So for each of these different, those 3 different options, reduce the loading, the imposed loading significantly, ensured that we had 25% GGBS in the foundations, and in the case of the concrete frame, within the structure itself as well, and in the case of the steel frame, within the composite concrete deck. Reduce the structural grid to 6.5 by 6.5 meters. Really tried to minimize the amount of material we put into the structure as well. So with the concrete option, we had to look at the waffle slab solution. Within the steel solution, had a look at reducing the thickness of the metal deck to 0.9 millimeters. And then in terms of the timber solution, we actually didn't look at the LVL solution as well. This is because when you look at the LVL solution, you need to put plasterboard on it to achieve that 60-minute fire rating. So what we did is we actually kept the grid, we kept the slab as CLT, but we increased the strength of the glue lam frame to GL30. And then we also introduced a hybrid solution as well. So we had a CLT deck on a steel frame to really show the importance of trying to blend materials where appropriate as well. And then finally, we had a look at shallow pad foundations as well. So in summary, the cumulative impact of good decision making drastically decreases the embodied carbon of your solutions. And that's without, looking at newfangled technologies. That's pretty much through conversations as a project team together to really interrogate and to question design decisions and design assumptions so that we can really reduce the embodied carbon of our buildings. So designing out carbon as material agnostic, thoughtful and efficient design using only what is necessary to achieve the required performance is key. In summary, I think this double triangle diagram, that's what I call it, produced by the Institution of Structural Engineers covers it quite well. Use less stuff. A lot of the design decisions that I went through previously really focused on material reduction. And as a way of focusing on material reduction, we could kind of look at that in a slightly bigger system as well. Do you need to build as much space as you believe that you need to build within the structural brief? Within the brief. Could you look at retrofitting? Could you just challenge the need for a building to form the solution that you need for the problem that you have in the first place as well? Looking into things such as building less and building nothing. And also to really sort of hit this home, this particular graph produced by the World Green Building Council in 2019, where when you're looking at the potential to build nothing and build less, it means that we need to think about those kinds of potential solutions really early on in project stages as well. By the time you get to the design, we've already made several assumptions that a building is needing to be built. And it makes sense to have these kinds of conversations about embodied carbon a bit earlier on as well. So thank you very much. I'd love to hear from you on the other side of the world. I've provided my email address there. Happy for anyone within this audience to get in touch about anything that they've seen within the slideshow or anything wider about embodied carbon and structures. And to be honest, I look at other embodied impacts as well. Really interested in looking at biodiversity impacts of our materials that we use. And I also discuss a lot of these kinds of topics with other disciplines that Buro Happold has, so our infrastructure engineers, facades engineers, etc. So please don't hesitate to get in touch. Thank you.
Well, not too much for lunchtime, I hope. I mean, it was fairly technical, wasn't it? Probably not what one normally expects, but I guess it's a really simple message that it's about having the conversation with the right people, in this case, a structural engineer. And they're the conversations that I'm not sure that are currently business as usual across the whole profession and the whole of the construction industry. But it's a very simple conversation to be had, as long as you've got someone in the room who can speak some of that language.
Thanks everybody for being here. I've titled this talk Pragmatic Optimism, an Architecture of Tomorrow. Pragmatic optimism is an attitude that I think architects in general are a pretty optimistic bunch. We kind of have to be because we project forward into a future that's not yet known. And pragmatic optimism in this context is really about how we go forward, how we do that in relation to the planet. So what I'm going to cover, I'm going to carbon in the very highest level. Why is it an issue? What's architecture's part in that? Where is it in buildings? And then I'll break at that point, and when I come back, I'll talk about how we do design differently and what the future might look like, just some hints and suggestions. Like Ross, I'd like to start with an acknowledgement of country and acknowledge the Whadjuk people and the Gadigal people of the Eora Nation on whose land my studio is. or our studio at Fitzpatrick and Partners. I'd also like to echo Ross's point about the connection to country as an opportunity for architecture to really think about its place in the world, and the connection that we have to caring for country as an attitude as to how we might guide ourselves through the next few years of what will be quite a lot of change in the way that we practice and what we want to try and achieve and how we understand what it is that we do. So in that light, understanding what it is that we do, let's start with this big globe that we've got that flies through space. Our planet exists with it for all of us, and we can live here because of the atmosphere that we've got that surrounds the planet. Think of it like Goldilocks' blanket. It's just right, okay? It's in balance, it's perfect, it's just right. Now, it allows in enough sunlight that heats the planet, and it retains enough of that heat within the planet to keep us all at a temperature that we're broadly speaking happy with. What happens is we push more and more and more carbon dioxide and other gases, other greenhouse gases into that atmosphere. We effectively insulate our blanket. We get a blanket with more and more and more insulative properties, and we upset that balance. It started by being called global heating, and we all know that it's really about climate change and that the change isn't always predictably hotter, but we're basically baking the planet, and we're disrupting that balance. So today's talk is really about how do we as architects deal with that? What's our role in it, and how do we go about it? So the first thing is to understand that climate change is just one of 9 planetary boundaries that scientists have agreed on. This is the current state of those boundaries. You can see the green area is the safe zone, safe operating zone, where the planet's happy and we're in balance. And 6 out of those 9 planetary boundaries have already been crossed. And in fact, climate change is not the worst of them, it's not the furthest of them, we're actually way beyond on a lot of other levels as well. For context, here's how that progress is happening over time. So on the left-hand side of the page, you've got 2009, where 7 boundaries were assessed and 3 were crossed. In 2015, 4 were crossed, and we're now on 6 being crossed. So you can see the trajectory of change at the moment is pretty radical and pretty quick. It's got a lot to do with the fact that we live in the Anthropocene, the times when humans are making an impact on the planet as well as that natural order. There's always climatic balance, but we're influencing it too much at the moment. Where we need to live is inside the donut. And this is a straight take from Donut Economics, great book if you can get through all of the economics bit. The ecological ceiling is the outside edge of all of that stuff that we've just been talking about, those 9 planetary boundaries. And we need to have a social foundation, which is that we need, energy, access to energy, water, food, education, income, safety, all of those items. So we want to live inside the donut, and in that donut is the safe and just space for humanity and a regenerative and distributive economy. So charging into the detail, and hopefully some of this is visible on the screen, this is where greenhouse gases are in everything that we do. So that crosses energy production, food and agriculture, land use, industry, transport, other energy sources, and buildings. And buildings in that is a relatively small piece, but you need to also recognize that buildings also have an impact on about half of that electricity number. They have an impact on land use and deforestation. They have an impact on industry around metal usage and cement usage in particular, an impact on transport. So it's really very connected. If you take that diagram and you take it one step further, remove the land use for a second and just look at energy, you can see that, and this is a diagram I'm sure a lot of people will be familiar with, about 39% of all of those sources of energy are in buildings, are trapped in buildings. 28% of that is what we call operating energy, and the other operating carbon, and the other 11% is embodied carbon. So the trajectory on the right-hand side is where we're headed if we just carry on, and it's just continuing to go higher and higher and higher and getting worse and worse and worse. We're effectively adding more and more insulation to our blanket, and what we need to do is get down to what we all know as net zero. That's a pretty stark line and a pretty dramatic line. That's not there to try and scare anybody. I don't want anybody to feel like panic is the right approach. What we need is that pragmatic optimism to say, okay, we know where we need to get to. It's going to be a bit of a radical change, but let's set a course to where we need to be and get on with it. So one of the biggest challenges for all of us is going to be education. It's going to be starting to develop an intuitive understanding of where carbon is and where it isn't. In part, that's going to be about learning some of the basics around what carbon is, where it is in buildings. So this diagram breaks it down from left to right into the product stage, A1 to A3, construction stage, which is A4 and A5, in-use stage, operating carbon, end of life, and then on the right-hand side, a circular economy, recycling the building. Whole life carbon, which is the whole life of the building, goes from A1 all the way over to the edge of the circular economy on the right-hand side. That covers off everything. And it's, in simple terms, made up of the embodied carbon, the carbon that we make things from, and the operating carbon, the carbon that we use when we plug in a light or a computer or whatever. Another way of looking at that is the names along the bottom. The A1 to A3 stage is cradle to gate. The upfront carbon stage, so A1 to A5, is cradle to practical completion. You will have heard of cradle to grave, which is the full whole of life phase, and cradle to cradle, which includes a circular economy output at the end where we don't just dump stuff. So there's a lot in that slide, but if we look at it like that, it feels like they're all equal. When we go to here, we get a sense of the relative size of each of those pieces. So on the left-hand side of the diagram, A1 to A3 is broadly half, so that's the product stage. A4 and A5 are actually quite small bits down the bottom. B1 to B5 is the operating of the building, not in an operational energy sense, but the use sense. So that's renovating, that's changing things out in the life of a building, putting on a new facade or adding additional insulation, changing out mechanical plant, etc. And the C1 to C6 is up the top. So you can see that the A1 to A3, which is the bit that as architects we all deal with, that's about half of that total number. So now if you look on the right-hand side of the page, you can see where is that half. And this is really to get everybody's mind into the superstructure is about half of that half. Substructure is the next biggest number, then facade, then MEP, and then internal finishes. Now that diagram is based on an office building. It varies by use and it varies slightly and the numbers do move around a little bit, but fundamentally, from first to last, those components stay the same. When you look at them in terms of their potential, the top of the diagram here, you've got the blue outline, including white area, is the embodied carbon baseline. That's where all of those materials are today. And the blue is speculation from Letty as to how quickly, what we can do to take them down. What we can do if we do really, really well, how can we reduce things? So you see the biggest opportunities, let's call them, are upper floors, foundations, frame, piling. That's all structure. That's basically in most buildings in Australia, concrete and steel, sometimes timber, but it's all structure. The next one underneath that is the envelope. And if you add all of those together, that's the basic building blocks of raw architecture before we start to add interiors and other things to it. And then the rest is interiors. The interiors, we can spend a long time chasing that stuff, and I'm sure we'll need to. But up front, let's deal with the big picture first, which is those structure and facade elements. And I think that's where we're going to go next. All right, I'm going to go through kind of two broad topics. The first is tactics that we at Fitzpatrick and Partners have kind of developed for ourselves, picking and choosing from loads of different places. And the second is then some case study projects that we've run through. A lot of the same stuff, a lot of the same thinking, expanded a little bit. First thing that will be very similar is this idea of when to do this. This is Ross referred to me as, mathematically aware of all of this stuff. I'm very much a fat pen architect. I'm the front end of projects. I love seeing projects through, but I'm very much the front end. This is a lead design conversation. This is not a detailed conversation. It has to happen up front, exactly like that last slide that was shared. Lead design, by the time you finish schematic design, you've baked 80% of the embodied carbon. In fact, 80% probably of the whole life carbon of a building is locked before you get to DA. So very much is a front end proposition. Some of our strategies, the first is the most important. Question everything that you've heard, all of the numbers you saw on the page, all the numbers I'm going to show you, question everything. There's assumptions that lie behind it. It's not that people are trying to lie to you or tell you things that are wrong. They've made assumptions, they've put in place ideas based on a set of criteria, and it's sometimes not relevant to you directly. Be careful what information you base your action on. Focus on the big wins first. That's why I'm going to talk largely about structure and envelope. Devise actionable approaches to remove or reduce carbon, and be careful of unintended consequences. Being really myopic about embodied carbon can often see you with a problem somewhere else, operating carbon, biodiversity, something else. You need to really be wary of the rabbit holes. So across the top of the page is kind of more or less the same graph in a different format. Highest impact, build or not build. Then as you move kind of from low to high or early to late, minimizing building size, extending existing building life, targeting structure, targeting enclosure, and then looking at products in terms of EPDs, etc. Not that that's not important. It just isn't going to save you anywhere near as much as the decisions you make at the start of the journey. The diagram at the bottom is another way of looking at that. Build less, build light, build wise, build low carbon, build for the future, and build collaboratively. The collaboratively thing with my Architects Declare hat on is really, really important. The reason I'm here talking to you is we've got to share this information. We can't do it. None of us can do it on our own. It doesn't matter how famous or how big your practice or how many people you have working for you. You can't do it on your own. We have to share. And we have to share not the marketing stuff. We have to share the tactics and the real life case studies. So I'm hoping for some questions later. From our point of view, I went to a presentation a while ago of the launch of a couple of books actually on embodied carbon, and I went with my wife, who's an architect but isn't as, I suppose, focused on this space as I am. And after the presentation I said to her, right, easier or harder? And she went, oh gee, that looks hard. And that's the problem for lots of people sitting in the audience. You go, there's a lot in this. So I wanted to try and break it down and get to some really core fundamental things. Accept responsibility. Stan Grant at the Institute of Architects conference last year said that architecture starts with an act of violence. That's really rough for an architect to hear, but it's a fact. Whether it's cutting down a tree or digging a hole, what we do causes harm. We need to understand that. We need to accept that. Again, not with fear, but with pragmatic optimism that we can do better. We need to not let that be a barrier to us making any form of change. We need to learn as we go. That's constantly having that inquiring, curious mind. That's really important. Get measuring, which is what was talked about last year, I think, is really key. You can't manage what you can't measure. Understanding the supply chain. What's the difference between supplier X and supplier Y? Why have they got two different numbers? What's in that number? Is it a difference in the way that the product is made, or a difference in the way the energy source that's used for the product, or what creates the difference? Again, that's about conversations. All of this is really just talking. Remember the rabbit holes. You can disappear down a rabbit hole, think you're doing the right thing, come back up and realize that you've created some harm somewhere you hadn't intended to. And finally, sharing and advocating. You're going to hear me say that quite a lot. So for us at F&P, this is a list of all of our projects. They're probably all burnt out and you can't read it. But in essence, it's every project that's in the studio or has been of late, where it is, its ratings, the year it's designed, the typology, the size, and finally, its score on a journey to regenerative design for us. What's it helping us move forward on? And every project's got a different story to tell. We use this to hold ourselves accountable across projects, okay? So let me dive into a case study. This is a building that we designed in and around lockdowns. So it's actually a 3-building proposition. It was a generic office development. It was 45,000 square meters all up. The first stage was about 18,000. It's in Sydney, so climate zone 5. It was 5.5-star neighbors, so pretty good. Site's a bit awkward in its orientation, 45 degrees to north, and there was a focus on optimizing carbon. We do these kind of diagrams for every project where we just highlight and are able to show the things that are a focal point on that particular project. Some are more important than others. In this case, low embodied carbon was kind of one of the key things. We developed with Australian Architects Declare and with Sydney Uni, a student from Sydney Uni using eTool, we developed a base case option for the structure of this building. Once we decided how big the building needed to be and where it fitted on the site and all those other things, we decided a base case scenario, which was actually a 9x13 grid with a big backspan. And then we ran an embodied carbon number on that, or our colleague at the university ran an embodied carbon number on that through eTool. And then we did a whole series of options. We partnered with our structural engineer and did a whole series of options. So we went from 9x13 to 8.4 by 8.4. and we went from concrete to all timber, just why not? And then we went from there to timber with a concrete core, which was a bit more of a buildable solution. Option 2 was an entirely concrete solution, but 8.4 by 8.4, not 9 by 13. And then we went down some single span solutions as well. One option that went the wrong way, which was a bit of a surprise. I guess the point here is even option 2, which is concrete, to reinforce what has just been said, the 30% saving in it by going from 9 by 13 with 4 meter backspans to an 8.4 by 8.4. Now an 8.4 by 8.4 is not very exciting, it's a pretty boring grid. And actually what it meant was we put a row of columns in the facade and we put a row of columns in both end facades, so it actually was a column less on every floor plate because the other columns had a big backspan on them. It meant that we had more solid component in the external facades. So we had our window wall ratio all starting to go in the right direction. Previous option had big backspans and gave us floor to ceiling panoramics. So it actually had lots of knock-on benefits. And we ultimately ended up pursuing the timber option. So that's the option we ended up with. It saved 62% on the previous assumption on the base case. Now the big learning about this was in order to simplify this process, and because it was the first time we did it from ground up. And then we've rerun the numbers later on including the basements, and it's a good deal worse. I'll touch on that later. We wanted to do this, but this is a terrible slide, by the way. Don't worry about it. We wanted to do this process on all of our projects, but it was a 6-week exercise, and we had to work with a student at the uni, and how could we figure out how to do that? What we ended up doing, we had the luxury of a bit of time. We developed an app. The way that and you can see it at the top there, www.embodied-carbons.com. Go look it up. It's freely available to everybody. We use that app to be able to take data from the ArchiCAD model. We use ArchiCAD, but it doesn't matter. You could use Revit and the same thing. Publish out a schedule, drop the schedule in here, and it immediately tells you across internally for us 3 different databases. On the external version 2, because one of them is information that we don't own the IP for. So the 3 databases were Greenbook, the Epic database, and the ICE database. It was really interesting when we dropped it in that they all told us different numbers, and we wanted to understand why, and that's about the fact that they're all using slightly different assumptions. So that's back to my mindset of question everything. Beginner's mind on all of these things. There's reasons why they're different. You just need to get into the granularity and understand them. We then use that tool to be able to play with things like the concrete content, whether it's 50 MPa concrete or 40 MPa concrete, whether it's got GGBS in it or fly ash in it, whether you change it in the walls, floors, slabs, cores, whatever. And there's a live little dashboard there that'll tell you what changes you're making. All of that is after the grid and everything else is already set. And the really interesting thing is all of those changes are very incremental and very small. Back to the point that was made earlier, the grid, the efficiency of the structure is the biggest thing that you can do. And that's not rocket science, that's just volume, right? How much of a material have you got? How heavy is your building? What we've used it to do is to create a bit of a chart for ourselves of all of our projects. So the green line is, you heard earlier referred to LETI, the London Environmental Transformation Initiative. It's a bit of a mouthful. They've created a series of benchmarks. That pink line is their benchmark for office. Almost all of those buildings are office buildings of ours. We've extrapolated it out for the amount that should be in the structure, and we've assessed all of the structure. So the good news is, relative to the ICE data set, which is the one that LETI uses as well, most of our projects are actually sitting below there. Now, the reason that most of those projects are sitting below there is, on the left-hand side, it's timber. In the middle, it's middle couple are a reuse of an existing building. There's something wrong with one of them because it's a 50-story building with a huge cantilever, so I still can't believe that the numbers on that are right, but anyway. And there's a few more timber ones, and there's one in Perth. So what I'll do now is go through 2 more case studies. This one is an existing building in Sydney, in Bay Street, in Ultimo, between 2 heritage-listed buildings. When it's finished, when we finish doing what we're doing, it'll look like that. At the moment, it looks like that. So council actually have referred to this as a detracting asset in a conservation area and wanted it pulled down. We came along and we said, well, hang on, we'd like to keep it, but obviously we want to beat the ugly out of it, but we'd like to keep it as a building. and we want to do so for embodied carbon reasons. The client was open to the idea, but I won't say they were kind of totally committed to it. What got them across the line was, because we kept the existing building, it was a 1960s building, it had relatively tight floor to floors, we were able to sneak an extra floor in on the top of the building. So we gained about 750 square meters. Our client went, golden, thank you very much, we like that. In doing so, that led us away with two things. One, we kept the existing concrete and the existing floor to floors. Two, we built on top in timber, which was lightweight, which meant that we needed to reinforce the foundations less. As we've gone on, foundations don't exist. So we're still having to create some foundations, but we didn't know that at the time. So this is, again, one of those slides where we talk about all of the things that we're doing on a project and try and encapsulate the sustainability moves. The big one here is the embodied carbon piece of keeping the existing and building on top in timber. The result is a building that council are very happy with, fits into the heritage conservation area, responds really well to its two neighbouring buildings. But it also saves over 450,000 kilos of CO2 by going in timber. That's just the move timber versus the equivalent in concrete. The bigger saving by far, by a factor, is that we kept the existing building slab below. So anything that you can do to keep a building and build on top, not necessarily going to save you money, it's going to save you carbon for sure. And so reusing the existing lower 4 levels of concrete saved an even greater amount. I've already said that. Right, last one. How am I going on time? Pretty good? Pretty okay? Nearly? 7 minutes, okay. This is in Perth. This is the other reason I'm in Perth at the moment. Great client. This is a carbon case study as a very small piece of a much bigger pie. So this is a project that's doing Living Building Challenge. I'm sure some people in the room will know it. It's Green Star on steroids, for want of a better kind of proposition. And it's about as complete a sustainability framework as you can get. So it crosses over everything from place, water, energy, health and happiness, materials, equity, and beauty. Beauty codified in a ratings tool is an interesting conversation, but it does exist. The point I want to pick on today is the embodied carbon footprint of the building and what we did in relation to that. That's the topic of today's conversation. In that, we also the building is producing 105% of its own power on site. It's going to be 100% water sufficient. It's the performance of the building envelope is nuts, which has radically lowered the amount of energy necessary to heat and cool the building. We're overall aiming at about an 80% reduction in embodied carbon, which is really, against a benchmark. Again, be always cautious when you hear numbers, particularly percentages thrown around. But it's true, trust me. We're reducing the amount of cars involved in the project, encouraging people to use public transport and cycling. We've got 10% of the roof of the site area is given over to urban farming and urban agriculture. There's a whole pile of additional elements. There's actually a 2-day workshop that I'm in the middle of, I just stepped out of to come and talk to you today about all that. So, let me just take a breath. We've gone from looking at structures on, like, take the full building, work it all out and do the structure. And we're now looking at just 2 grids of the building. This is the ground floor slab. We had to do it in concrete because it's fire between car park levels and the levels above, a car park level and the level above. So 2-hour fire rated. So we did it in concrete for 9 different options over a 2-bay grid, and we just ran the numbers on each of those options. You probably can't read those numbers, but the biggest one is 73,423, and the smallest one is 20,000. That's across everything from a flat slab, a banded slab, steel structure with bond deck on top. One of them's brick vaults with a concrete slab on top of that with steel below. And in the first round, the lowest one was about 20,000 kg. That was the bubble deck solution in option 8. When we went from conventional steel and concrete to conventional steel and a geopolymer concrete, that number dropped from about 20,000 to about 10, just under 10. And then the other option that became available is option 3, which is concrete with pedestals. We then went to what happens if we use recycled steel and geopolymer concrete. So we got all of our materials ducks in a row. What does that then end up with? And the lowest we got to was about 7,000 kg for that same slab. That ultimately we didn't do because the recycled steel we couldn't get certified to be reused in a structural sense. So we ended up at 9,000. But ultimately, the solution for the slab was less than 40% of the conventional approach and only 13% of the worst solution out of all of the, apples for apples solutions. It's still 30% more than the lowest carbon option because we couldn't get that steelwork to work. Looking at the diagrams on the right, that's basically looking at the model through materiality and just trying to say, where have we got the material in the building? This is the same thing. This is an exploded axonometric. Blue is concrete, red is steel, and yellow is timber. In my mind, this is a timber building. Have a look. Does it look like a timber building to you? And that's the reality of what's below ground, right? The first floor the ground floor is the one in the middle, the blue one in the middle, and everything from there up is timber. The two other diagrams, the one in the middle talks about the embodied carbon per level. So you've got basement 2, which is really a water tank and piles. Basement 1, which is the big one in the middle, that's piles and a lot of concrete. Then you've got ground floor, which is a ground floor slab in concrete and a tiny little bit of yellow. Level 1 is the vast majority of its timber. Level 2 is almost exclusively timber. And then the diagram on the right-hand side talks to the elements. So the one that's really high in the center is the piles. So really surprisingly for my timber building, almost all of my carbon is sitting in the piles that are allowing me to build it in the first place because I've dug a basement. Unfortunately, we found this out we were pretty committed by here. We were past DA and a few other things, but it's interesting. So what could we do about it? We went from conventional concrete would be the dotted line at the very top. This is assuming a boral Invisia, which has got a 40 MPa boral Invisia, which has got a drop on it. We then are doing a really, really interesting exercise with BGC on testing a lower cement component again. And all of the concrete, I should say, all of the concrete on this job, and indeed the rammed earth walls on this job, are all using the material off the site. So we're excavating it out and we're putting it back in concrete and putting it back in rammed earth. BGC's option lowers it all again. And then if we went to the Wagner product, we would go lower again. That's proving to be difficult, but we're still looking at those two exercises. And basically this is about, I don't care what the number is. The number is not important. Which way are you going? Are you going down? Keep going. The goal is 0. You won't get there. That's okay. Get going towards it. This building also has got a lot to do in material circularity. God, that's washed out. I hope it's not as washed out for you. But this is just talking to some of the material propositions that we've got going on. Avoid using additional materials where you can. So that's don't use. Reuse or recycle product. So either reusing the material from the site or recycled timbers, etc., that we're using. Using biogenic materials, so anything that stores carbon. And yes, there's an accounting thing about whether you can or can't count it. Don't worry about that. It stores carbon. It's better than something that emits carbon. Simple. Lots of biogenic materials, lots of local materials in the building. Where you have to use something like an aluminium, unfortunately, we couldn't get away with a timber facade. Reusable and recyclable. How reusable, how recyclable? So if it can't be circular on the way in, can it be circular on the way out? And then the last of those is really important, design for disassembly. Designing for disassembly means that the building has a life after you're finished with it. Or if it needs adaptation, it can happen without throwing everything in the bin. Little plug for Architects Declare. Anybody who's not a member of Architects Declare, please consider it. The Architects Declare 12 core principles are a really good guide and kind of starting proposition for people to be able to think about. Don't just become a signatory, become an active member. We always need more of them. Sharing, this is where I talk about the future. Sharing is really, really important, right? You've got to if you've got a good story, you got to get out and put it up. Even if it's not a great story, you got to put it up and talk about it anyway. Talk about the things that worked and the things that didn't. Breathe have got some really great stuff on their website that they've put out recently from a talk that they gave in-house. So sharing is really important. And I always finish on this quote by Maya Angelou. And this is kind of, I suppose, the opposite of taking responsibility. Not, it's balanced with taking responsibility. Do the best you can until you know better. And then when you know better, do better. It's as simple as that. So we don't need to beat ourselves up about it. We just need to do better.
I love this stuff, and I particularly love that it's coming from someone like Paul, the fat pen guy, that through the commitment to the challenge has become very conversant. So he's not an obvious candidate for knowing more about the maths and science than anybody else I've come across.
My maths teacher would agree with that.
But he's done that by deep diving into it, and I think there's a fantastic role example for all of us that we will all have to become like that. Some are further on the journey than others, and there's the challenge, and the great thing about it is it's both complicated and it's simple. I mean, in essence, it's simple. The complexities of driving to finite numbers is more complicated, but you know, 0 is a number, and I think that's the challenge. We have to be thinking numbers of some form to think we're ever going to get to 0. So measurement is fundamental. So I would like to also say that our sponsor for today is Kone. I'm not sure if your boss turned up, did he? Managing Director. Thank you very much, sir. Thank you for helping us out. That's terrific. So we're going to have questions and answers now. So we've got I'm going to do the roving mic thing, and Paul will get the job of answering most of the questions. I might be able to kick in on something at some point, but we'll see how we go. So, any questions? There we go. So we have to do it. So we have to do it by mic, otherwise we're not going to get it for the recording. So please be patient as I deliver you the object.
What if I was trying to avoid being recorded? Thanks, Paul. Great presentation. You mentioned when you were looking at your self-assessment of your projects that you were measuring or doing, I guess, a subjective measurement on your progress towards regenerative design. I was wondering how you define that, what it means to your practice.
It's a great question. Actually, it was something that we're doing a workshop at the moment with the Living Future Institute, and I asked them that exact same question yesterday, because it isn't clearly defined. Regenerative is ultimately that you do less harm, that you don't just do less harm, you actually create a positive outcome. Netted across everything, it's a positive outcome. The definition of exactly what that is and how that is really hard. But to me, it's more of a mindset, right? Accept the reality and don't greenwash, but accept the reality that you're not going to get there tomorrow or the next day. We will ultimately, but we're not going to get there in the short term. But it's still the flag. The way we treat it in-house is it's the flag on the hill. It's where we're aiming at, right? We won't get there, and we don't need to get caught up in are we or aren't we? We need to be making progress in a direction. And that's where, I guess, my kind of starting point about pragmatic optimism. The optimism is that we'll get there. The pragmatic is that you can only, as I said to my son from time to time, how do you eat an elephant? One bite at a time, right? So that's all you can do. You got to just keep taking the one bite at a time.
But I think the pressure is building though, because with ASIC's requirement for mandatory declarations of Scope 3 emissions for large companies July this year, that's going to bring a whole bunch of our clients into the frame of having to declare their Scope 3 emissions, and they'll be looking for consultants who are expert in this stuff. So it's a fantastic opportunity, but there's also a liability if one lags, and there's a whole bunch of other financial pressures coming. There's green finance, and we'll be talking a lot more about this stuff tomorrow, actually. So tomorrow's session is going to focus on that as another driver. Another question. Mark. Thanks.
Thanks, Ross. Thanks for the great presentation, Mark from Hesperia. I was really enjoying the message that targets are great. We all want to get somewhere, to 0 at some point, but we really just have to start doing everything we can about everything we can. Like, I feel like that's the growing up message that comes through, and I really appreciated that. But I was wondering about being an architect. You're a little bit dependent on your client, I would have thought, and how you go with that, whether the clients are driving you to some extent, or if you have a pitch for them that you find effective.
question coming from a client.
Yeah, no, okay. Well, I won't. You put me on the spot to give you a pitch, but the simple answer is all clients are different, right? So the client on the Perth project is awesome. They brought us Living Building Challenge. They forced us to go down that path. Well, didn't force us. We happily jumped on board, but they wanted to go down that path. So that journey has been very, very different to a normal project. The project in Sydney, the lever was me understanding what they want and trying to find a way to do what I want within that. And that was not just giving them the square meters, it also was about the approvals process. So by aligning the building, the things I didn't mention, that building's also 100% electric. It's ready to go for a green power agreement. Sydney City Council has a strategy around net zero. They want green power, they want fully electric buildings, and they want embodied carbon lowered. That's their published document. So we basically just fed back to them, here's a building that does what you want. Guess what? We got a quicker approval. So we got the client more area, we got a quicker approval, we had council on board. Who doesn't want that? And then the outcome was, we have a fully electric building that's got natural ventilation strategies embedded in it and has a hugely lower embodied carbon number. Win, 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 win. And ultimately, that's our clean pitch. Does it work with everybody? To a level, to a degree, it allows you to push to a point, and then there comes, the dollar question about doing it this way versus doing it that way. And you've always got to be nimble enough to be able to respond to that, not to be completely dogmatic and just stick to your guns. We've got a project that we just finished this year. It's 2017 as a job number. I actually started on the same site in 2006, so it's been a hell of a long time. The problem with our project, or the opportunity with our projects, is that they do look that far ahead before you start to occupy it, before day one. So you have to think the trajectory that everything that's been happening over the last 20 years is only going in one direction. We're getting more and more and more sustainable. So if you've got a building that you want to have ready for 2030, you better aim for the stars, and maybe you'll hit the post box. But you got to aim out that way. And then the same thing if you want to think about financing on a project. If you want to hold on to a job for 20 years, you want the job to be valuable 20 years after you built it. Now you've really got to look at, what can I do today? What can I think about for tomorrow but not maybe do? How can I build a building such that it allows for future upgrade? All of those things are ways that the building can go on. So you got to understand your client, number one.
And green finance is becoming a thing.
Well, it's just another one of those things that's going to push us along that journey, right?
And the other, and this is, can't oversimplify it, but the story that Natasha told was essentially a story of taking material out of a building. Now that might involve slightly more complex formwork here and there, so it's not all dollars, but the more material you're taking out of a building, the more cost you're taking out of a building. So dematerialisation, in simple terms, equals reducing the cost. So if that frame keeps the way you think about it and don't overcomplicate it, then it'll yield that kind of outcome.
Thanks, Paul. Just in terms of meeting the requirements of Living Building Challenge in Perth rather than in Sydney, can you speak to some of the challenges of, say, finding locally sourced materials or anything else which has been particularly hard?
Yeah, so we've managed to get Living Future Institute to extend the boundaries of, so Living Future, for those that don't know, one of the things in Living Building Challenge is to try and get a percentage of your materials, 30% of your materials within the first zone, another 25, and then the remainder. And those zones are, well, for Perth, they're from here to the border, maybe. Then the next one is all of Australia, and the next one is most of Asia, and then the rest is the rest of the world. Finding local materials is a bit of a challenge, but strategies like using the material for the concrete from the site, the concrete was probably going to come anyway, but it's a great additional narrative. And LBC is a process-focused proposition more than it is an outcomes-focused proposition. It still wants the outcome, but it's very much about how you went on the journey. We've actually, through the LBC, have expanded those horizons. So the first zone, because Perth is quite so isolated, the first zone gets you more or less to the Victorian border, so it can include South Australia, which we did strategically for timber supply. The second one gets you all of New Zealand. The third one gets you all of China. So then, really that's about trying to source locally as much as possible. And it's also about the final place of assembly. So you might be bringing together a facade, for example. Our glazing is coming, the aluminium's coming out of Europe because they've got the dyes and the systems and a better thermally broken suite than we can get anywhere else. The glass is probably coming out of China, but they're getting assembled in Perth. So it's a locally sourced product from an assembly point of view. There's local labor in it, etc. Probably the biggest challenge in doing an LBC project full stop is materials. Materials are really bloody hard. The second biggest one in doing it in Perth is water. God, I wish it would rain here a little bit more. Getting water balance here is tough, really tough. And LBC is we're aiming at full certification on that project. So it's going for a tick in every single box. And that's a pretty extreme way of going about it. But it's more a pilot project to prove it can be done.
And obviously transport figures enormously in any kind of cut that one does across about where the carbon is. And
depending on more on transport method than on distance. So you ship something on a ship, its number for the individual item its carbon number is actually pretty low. If you ship, so we looked at timber from Europe versus timber from the East Coast, and then if the timber from the East Coast was coming on a truck, forget it. If it was coming on a train, it's pretty good, but the guys in the East Coast are going, but that's not the way we send it. Like, well, but we might want you to actually stick it on a boat as well and go around the outside because it's just a lot less. And that's because people don't think necessarily in carbon. And one of the things I really wanted to get across to everybody is we want to have this intuitive understanding of carbon where we make design decisions with carbon knowledge. We're not there yet, and it's going to take a period of time. It's probably going to take 3 to 5 years for everybody to start to get that conversant rules of thumb, gut feel, this is going to be better than that. You can then go and test it, but that intuitive knowledge will then see us designing more wisely in a carbon sense.
There's a great little case study story of a timber structure. You might know the Pingelly project, which is a lovely timber structure that was multi-awards 3 or 4 years ago. All that timber came from Melbourne. What they've now done is they brought the factory to Perth. So the later iteration of that project, if you want to make the connection down at Ravensthorpe, all that timber was cut and milled and dealt with here. So it's made a huge difference.
Thank you for that excellent presentation. Could you mentioned briefly about performance and the facade. Could you just expand a little bit in terms of operational carbon and the importance of, is that a passive house certified kind of performance level?
On the one in Perth? Yeah, it is actually. Well, it's getting pretty close. So we're doing some, the project hasn't started on site yet, but when it does, we'll be doing some air tightness testing, and certainly that's been in the brief. Not quite down as low as passive house levels, but not far off. And there's an awful lot of ventilation in it. The piece I was going to mention was about the first project, the one that we did the structure study on. We also did a facade study on that same project, trying to look at embodied carbon in sun shading. So the benefit being to the mechanical plant. And we theorized 5.5 neighbors is around X in kilowatts. Of that, around 60% of it, often in a normal commercial building, would go to heating and cooling. So that's the bit that we can target a saving on. We measured a whole series of different sunshades from 200 millimeters to a meter, and the impact of them, took that as a saving, and at the start put in the cost in embodied carbon. And the interesting thing, and this is the other point about context, is because the grid is greening as rapidly as it is, and we were looking in carbon, we weren't looking in dollars, so I wasn't concerned about how much energy we saved, I was concerned at how much carbon we saved. A decarbonizing grid, which Natasha mentioned as well, means that the savings actually tailor off. And what we found if we made the sunshades in aluminium, very high embodied carbon to start with, if we made them in aluminium, we never saved enough. In other words, by the time it flatlined, we hadn't passed zero. If we made them in terracotta, which was about, well, what we theorized was if we made them in half that number, would it cross zero? And it does very quickly. But that was a building that was supposed to be built, well, the model was done for 2021 on. If you did that model for 2030 on, even in terracotta, it won't get there. So we have to start thinking very differently about where we're putting carbon and what we're doing it for.
Just follow on. Does the Living Building Challenge value the indoor air quality benefits from a mechanical heat recovery ventilation system like you have in a passive house? And because of humidity and, you know, removing allergens and all that sort of stuff?
Yes, it does. It doesn't necessarily agree that that's the only method of doing it, but it does value it for sure. So there's an indoor air quality kind of measure that happens the whole way through. The point at which I left the conversation to come here, we were getting deep into VOC content and VOC emissions, and they're two different numbers, and what we have in our spec might not be quite right. We might need to adjust that before we finish. So yeah, it's a highly detailed and technical kind of piece on the one hand, and on the other hand, it takes the real simplicity, the philosophy of a tree. You know, a tree can only grow as big as it is on a site by how much water and nutrients it can take out of the ground, how much sun falls on top of it, and what it's restricted by or not. That's the simple philosophy of Living Building Challenge, and it's beautiful. Apply that to a building, and you can really see how you go to really interesting places.
I think one of the things we have to also be thinking about with regard to the implications of the greening of the grid is that it's diminishing the conversation anyway. It's perhaps the focus in many people's minds on lowering operational energy, because electrification of the grid and calling it renewable energy that's coming from wind or solar or something suggests that it doesn't have any kind of cost to it from an environmental point of view. But you know, the cost to environmental cost on all levels to produce all that renewable energy is still very significant, and it'll become a bigger and bigger factor in how we think about things. So we have to keep driving down the operational energy draw on buildings.
It's really interesting. So where we ended up on that project in Sydney was that we ended up with a sunshade. It was 300 millimeters, I think 250 millimeters in terracotta. So we went for the most efficient sunshade we could. We probably wouldn't have passed Section J unless we did. This was a building that already had a window wall ratio of 50%. It was already, you know, quite a way down a lot of metrics. But that was kind of a current compromise. And also, I suppose the conversation around energy becomes one about equity rather than about where its source is coming from, right? So if we've got a finite amount of energy and we're moving to a grid that's maybe going to be, well, there's going to be a lot more energy available, but energy is expensive, and why should this building take more than its fair share? So you should design efficiently, but you need to be mindful in carbon terms of not putting in more carbon than you'll ever save or take out. And that's a really fine kind of balance, but it's just by experimentation. That happened to be a job that we did at the end of the first COVID lockdown. So we had lots of people at home. We were all kind of, you know, in our own little bubble, and I was able to say, just spend 2 days doing that. I don't want to talk to you. I just want you to come back in 2 days' time and tell me what that graph looks like, and then we could go through it all. So it was a bit of a free kick on some experimentation for us. The big hard thing is, how do you get that into an architecture practice? How do you do that project by project? And my only advice on that is, there's only one thing in an architecture practice that's funded, and that's projects. So find a way. That's why I was showing the slides about what our strategy is for each project, because you want to try and bake it into the bit that you already have coverage for, rather than get the office to agree to spending 10% of your time off contemplating your navel in a corner. You know, it's, if you can get it on projects, you'll be better off.
Thanks. Fantastic presentation. I've got a question about the modelling process between the two case studies. We went from a whole building to just 2 bays. And is that an efficiency move? And then what are the consequences of not modelling the whole building on a project if it's just starting off with 2 bays?
So, really good question. So the reason that we started with the whole building and we built the app was to try and get to a number, right? And I guess what we realized along the journey is, well, what difference does that make? We can measure one project against another. Where we've been able to take it is that graph that showed each project against each other. And I'm able to call out the fact that probably the worst per square meter in all of it is a house that we're doing, which is a surprise. I still think the 50-story building's wrong, but the house is the biggest number, biggest single number, which is a surprise. We can measure, I guess, against each other. We can get a relativity. But other than that, it doesn't really matter, right? That number is not getting fed into anything else. And we've had this conversation about when financiers start to demand Scope 3 emissions being captured and embodied carbon being captured, loads of people are going to start measuring for that. And that's fine, that's good. And that'll get to a set of numbers, and those numbers will become real. Neighbours is coming out with an embodied carbon ratings tool that I think, like operating energy and water, that'll just become the default, and we'll all just follow along with Neighbours' method. But that's not very useful tactically to me as an architect working on a project. And the same thing is the grid. What's happening in the grid is context, right? It's like doing a decent site analysis. You would cover off, the grid is actually going to be, by the time we build this building, the grid is going to be 82% green. Therefore, I'm not going to worry about operational carbon. I'm going to worry about embodied carbon. So for us, tactically, the 2 bays was very quick and easy to do. We did that study across 9 options with a bit of backwards and forwards with the structural engineer in no time, like really in no time, because we had all of the numbers to plug in. It's a bit like a QS's schedule. It's a matter of how much times the CO2 of the element gives us the outcome. And then you just bundle that together, put it in a graph, and there you have it. That allowed us to be able to have a conversation with the client and the structural engineer, who was a little reluctant to go down the path we wanted to go down. And we ultimately ended up compromising on which way we went. There was lots of practical reasons. I'm not criticizing them for that. There was lots of pragmatic, practical reasons why the pure lowest number wasn't the right way to go. And sometimes you got to make those, to the question earlier, sometimes you got to make those pragmatic decisions. But we've, in a way, let go of trying to get to the complete number, because an LCAs are hugely important, but they're not tactically very useful for an architect working on a project. So that's really the move that we've tried to make, is what can we use that we can do quickly, that we can make a good decision. So our embodied carbon app is only a design tool. So we don't use it for construction end decisions. So we don't include a lot of stuff about individual EPDs, for example, in there, because at the front end design, you can't make those calls. They're calls that you make at the back end of a project. So yeah, right tool for the right time, I guess.
Yeah, I think the thing about certification, whether it's Neighbours or Green Star or whatever, I mean, I think the takeout that I get from the way you talk about this stuff is that it's about thinking at a conceptual design stage, thinking conceptually about carbon. And then as we get more and more sophisticated, the whole certification thing will become a bigger and bigger part of our lives, because more and more clients will be after it. I mean, personally, once I was introduced to life cycle assessment by friends at eTool about, say, 4 years ago, that was a whole new aha moment for me, that you could actually measure it, you could model it. And I think one of the great things about becoming conversant in life cycle assessment is that it starts informing your decisions conceptually as well, because the numbers start become part of your intuitive thinking. And I think life cycle assessment is a terrific pathway to that. So I mean, for my part, I'm a great advocate of life cycle assessment, and working in the initial stages of a project to set yourself up for what could be a full whole of life carbon assessment when you're a bit further down the track.
Let's be controversial for a second. I'm going to agree and disagree. So that my agreement
sitting right in front of Mr. Eatool
right.
here as
that's
well.
Okay. That's fine. I didn't notice this, Sarah. The best thing about life cycle assessment is when it's least accurate. So when you do a life cycle assessment, if you want to get to the absolute granularity, fine number of everything, you got to plug in everything. And you got to have the data on not just its timber, it's this timber from this place with this EPD, and you got to try and do that for everything. And that you need to be way down the project. You're at the end of the project by the time that happens. Where, and I'm sure you're going to agree with me, where LCA is most valuable is when the numbers are generic and they're guides. But these guys can come around and go, here's 10 things that you could do that are going to change your number, are going to change your proposition. And they're telling you that at a point in the project where you can still do those 10 things. You're not finding that information out down here at the end of the project and then trying to wrap it back in to decisions that need to be made at the start of a project.
Yeah. And I think that's the emphasis about thinking design, not certification.
It's
Until
also
we all get much, much better at this.
Yeah, it's also the mindset about don't worry about the granularity of the number so much as the intent and the direction. Because to get to the granularity of the number, you got to put in everything. At which point, it's too late to make the design decision to do it. You could pull apart an LCA that you finished on a project for a finished job and learn the lessons for the next job, but you can't really learn those lessons for this job because you've done it.